Hello everyone, my name is Tobias Schwartz and I'm excited to shortly talk to you about my work with colleagues Sioutis and Diedrich Wolter. Together we are interested in the question of how to do robust planning in the face of a dynamic execution environment. And here we present the work called Towards Robust Constraint Satisfaction in Hybrid Hierarchical Planning. So let me briefly demonstrate a running example that we might use to illustrate what we mean with robustness. And for that, consider the following train network. So we have trains starting at station S1 and they should drive until station S3 using this train network. Stations here are denoted by nodes and the edges between those nodes are the different paths they can choose, and they clearly are indicated using an arrow so they have a one-directional path. And the shortest path then obviously is the one via S2 here at the top, which might solve the problem quite quickly. However, we also have a different option, and that is using S4 as a start, and then we have two more options, S2 and S5, leading to the goal to S3. And here's already what we first want to note, that there's a difference between a flexible and robust solution. Let me briefly show you the definitions and then I'll illustrate that at the example we have. So robustness would we define as the ability of a system to resist all possible changes given by a model, whereas flexibility is the ability to quickly generate a new solution in case of change. In other words, robustness might be seen as a proactive measure, whereas flexibility is rather seen as a reactive measure. So going back to where we are here, at S4, if we are here, we would have two options to continue, and if we follow a least commitment approach, then we could say that we are more flexible here in S4 than we are, for example, in S2, because in S2 we only have one more option to continue to S3. Whereas a robust solution would be a plan from start to finish, so either this one or any of those, that we would define in prior based on some model of the environment of some potential changes, that we say, okay, given those changes and the likelihood, this is the most robust plan. And clearly it's not too easy to define, because we don't necessarily know how change may be modeled. Right, so it could be based on some probability. We could know that some effect happens with some certain probability. It could also be modeled qualitatively or quantitatively. And it is also important to know when those changes are known to a planner. If we want to find a solution here, and there is some change occurring during plan execution, then that is obviously different from some change that we know prior to planning. Right? If we already know before we start planning that the link between S2 and S3 is not available, we won't choose S1 to S2 to S3, because that's just not an option, and the only valid option then remains the path down here. In partial order planning, we follow this least commitment strategy to achieve this flexibility, and here we can use a notion of stage relevance in classical planning, where we say a certain state might be more relevant to achieving a certain goal. And we can use that to find the most promising linearization. In essence, that then resembles sort of the idea we could have with robustness. That we say, okay, robustness is essentially the idea of finding the most promising linearization that might withstand any potential change. And usually what we see is that we combine flexibility with some form of execution monitoring so that we can then adapt the choices made during runtime based on current information that we have. And we've seen similar frameworks also in hierarchical planning recently with, for example, the refinement acting engine, where we have the task execution and also the reaction to external events. What we now briefly touch on is a little case study that we're interested in, and that is modeling the whole planning problem as a CSP, or more concretely as a Meta-CSP. And I won't go into the details here now really, but the key idea is that we can, in a Meta-CSP, model different forms of knowledge in form of different set of constraints such as temporal, causal, symbolic, spatial, so even qualitative constraints from infinite domains we can model within this constraint network. But also the plan and even the hierarchy imposed from a hierarchical planner could be encoded, and you could see something, a method defined down here below that I won't discuss in detail now. We chose this approach because we could model many different forms of knowledge that we find in real-world applications. For the sake now here, robustness could be defined following a notion that was recently introduced in the light of QCNs, that is qualitative constraint networks. And the idea here is that we compare the similarity of all satisfiable solutions. That means that we have solutions that are similar to others and thus have a higher probability of staying consistent at the end. That is at least the hypothesis. And a solution then consequently with the highest similarity over all valid options is then the most robust. And that is similar to kind of the idea of relevance in a way, because we actively can say which of my found solutions, in essence plan linearizations, might be the most robust according to this similarity definition. And we can use that prior to plan execution, and if we then know changes prior to our plan execution, we can react to them beforehand. Ideally we don't have to do any changes at all because we already chose the one solution that is most robust. But it could also be that we then still are able to change, and that doing quite efficiently because we have a set of predefined robust solutions that we might pre-compute or something. For example, in this train problem that we have here, we might not only drive this route once, but usually do that multiple times, right? So we have the plan layout set once, and then we drive the same route over and over again. And here it might be that someday we know that there's certain restrictions, there's some rerouting, and we can easily take that into account using such a design. To summarize, robustness has not been investigated in hierarchical planning before. We outlined the challenge of modeling robustness, sketch a notion of robustness studied recently in the QCN context, and outline how we could apply that in hybrid hierarchical planning using such a Meta-CSP approach, and hopefully with that start a discussion towards more robust planning.